triangles by their sides and their angles, like sails out on the high seas. Can't be right or isosceles. Oh, look at the foot of this goose. It's scalene and obtuse. When you break the pool balls with the cube, they're equilateral and obtuse. If you add up every angle, there are 180 degrees in a triangle.
Welcome everyone to 5.5 in our geometry curriculum, and we're looking here at another one of these special ways to prove triangle congruence. This one is by SSS, which would be side-side-side congruence theorem. So we've already looked at a side angle side, where you have two sides and then the included angle. That would be side angle side, or SAS. We're looking at the SSS here, and also another one which is the hypotenuse leg theorem, which that would be more specific to a right triangle on that one. So we'll look at that one eventually by the end. Alright, let's take a look at our little cartoon for today. So here it is. Why does this story make me so angry? As a bull is reading Red Riding Hood. Okay, so getting into our first core concept, our first theorem actually, I should say, is on page 145, and there it is, the SSS, and that's just fairly simple, straightforward. All the sides are congruent. If all the sides are congruent of one triangle, and then all the corresponding sides of a second triangle are congruent, then the two triangles can be congruent. That's what this is saying here. If three sides of one triangle are congruent to three sides of the second triangle, then the two triangles are congruent. So we can write out a congruent statement. But the important thing here is, as you're writing out your congruent statement, there is a right and a wrong way to write a congruent statement. And that's what we're going to see here in a minute about whether we have definitely correct congruent statements here. As you can see, it goes ABC is congruent to DEF. And so if you look at where ABC is, let's just take a look at that one first. So A, B, and C, and look at this, the little marks here. So you have your 1 here, there's 2, there's 3. So if you go from A, B to C, that's going to go, and if you go around the triangle this way back to A again, you're going 1 to, so you're going 1, 2, and then 3, that mark. And so over here, DEF should go 1, 2, 3 on this one. So D to E to F back to D is going 1, 2, 3. So we couldn't say, ABC is congruent to DFE. We wouldn't want to do that because that would be going 3, 2, and 1. Or even EFD. It would have to be the same way with the same congruent marks. So that's one thing to keep in mind as you're working through it. Always make sure you have a correct congruent statement. Alright, so here we are. This is what we're deciding. We're deciding whether the congruent statement is true. And so that's what we want to look at. We can see here on number 1. And just go ahead and watch these. You don't have to copy these ones down. This one's going to be like the first couple in our extra practice. But just kind of watch this and get the idea. But you have your two triangles here. You can see, yeah, there's the 1 marks, there's the 2, these are congruent, there's 3, those are congruent. And so this triangle, the first one here, says DFG. So if you travel around the triangle from DFG back to D, so you're going to go 2, 3, then 1. So 2, 3, 1. And so if we go over here, HJK needs to go in a 2, 3, 1 fashion. So H, then J, then K. So H, J, K, that's this way, 2, 3, 1, and it does exactly that, 2, 3, 1 fashion. So yes, that is correct for a congruent statement. We can say yes on that one. That is correct for the SSS. Number 2, if you look at this one now, even just on your diagram, we see, okay, there's 7s, those are the same. 9 is here in the middle, which is a shared side, so that would be congruent to itself, so that's a congruent side. But then this one right here, 3, is not congruent to 4, of course, so it would not work. There is no congruent statement you can say because these really basically just aren't congruent. That's what it says here, no, because they don't correspond. AB and CD do not correspond, they're not the same measure. So all the pairs of corresponding sides must be congruent for you to be able to say SSS. So just right there, that's a no, just because they're not even congruent. And then for number 3, we have this triangle starts off with Q, P, and T. And we notice the two triangles here, they do share a vertice right there at T. But we have there's the 1 marks here, there's the 2 on the sides, 3 is kind of in the middle. So let's just see if these would work. Q, P, and T. So if you travel around the triangle from Q, P to T, you're going 2, 3, 1 again. So 2, 3, 1 fashion. So RST should go into 2, 3, 1. RST back to R is 2, 3, 1. So yes, that one works as well. So we can say yes on that one also. All right, so let's take a look at our extra practice. Okay, so for number 1 and 2, we're doing exactly that. We're deciding whether the congruent statement is true. It does say explain your reasoning, but I want you to just right now figure out, is it true? So go ahead and try number 1 and number 2 and see it's either yes or a no. Is that congruent statement that you see there, is that true about the triangles that you have here and over here? So go ahead and pause the video and look at that and see if that's true or not true. All right, so hopefully you got an answer for 1 and 2, and you're saying either yes or no for these. So you can see the 2 triangles here. There's your 1 and 1, so 1 and 1. So these would actually be isosceles triangles if they have 2 congruent sides here. So these are congruent to itself. There's isosceles, this is isosceles as well. These are your 2's. So your base right here would be congruent to each other. And so this one says A, B, C. So A, B, C back to A. So 1, 1, and the 2. E, D, C should do 1, 1, and then back to 2 again. So E, D, C is a 1, 1, 2, and that's fine. So that would work. Actually, this has a possibility of doing it 2 ways, because you could have said C, D, E, and that would have been also a 1, 1, and 2 fashion as well. So yes, that one works out. So we can say yes on that one. You're given that these are all congruent sides, and so yes, that's kind of what the reasoning would be, that AB is congruent to ED, BC is congruent to DC, and CA is congruent to CE, and that's all the corresponding sides of our congruent statement. Number 2, we have a shared side here, which would be congruent to itself. So there's another congruent side. That would be like your 3rd side. So you have your 1 marks here, your 2, and this would be like 3 right here. You could put 3 on that mark if you want to. And so for this first triangle, or K, G, and then H. So K, G, and H, that way goes 2, 1, and then 3, that 3rd side. So 2, 1, 3. We would need to do a 2, 1, 3 on this side with H, J, K. So we have to start with H, J, and K. So it's a 2, 1, 3 as well. So that seems to work out just fine. 2, 1, 3 here, 2, 1, 3 here. And so yes on this one as well. Those all are fine. And we can see right here that HK is congruent to HK by the reflexive property. That's what you need to remember. Always a shared side is the reflexive property. Okay, so for number 3 and 4, do the same thing for these ones. Again, same question here. Just is the congruent statement true? So yes or no. And then go ahead and pause the video and decide that, and then play it to see if you're correct. Okay, so you should have a yes or no for these for 3 and 4. So here's our triangles. There's our 1 marks, our 2 marks are here, the 3 marks are there. So for U, V, and W, so he goes U, V, W, that's going to be going 1, 3, then 2. So 1, 3, 2 is the combination we need to have for the other congruents. X, Y, and Z. X, Y, Z, that way goes 1, 2, 3. So that's not the same as 1, 3, 2. So this one would definitely be a no. It's not the same. This is not a correct congruent statement. The right congruent statement, if you have a 1, 3, 2, would go 1, 3, 2 here. We go Y, then X, then Z. That would have been the correct one. That's what this is going to say. So no, this would have been the correct congruent statement. Shows you what's congruent here on the sides. So by the SSS, it should have been the X, Y, Z on the second one. For 4, so we do have a shared vertice right here. So you have your 1 marks there, the 2's are at the ends, and there's your 3 marks. So RST, so RST goes 1, 2, and 3. So 1, 2, 3 is the combination. RPQ needs to do the same thing. So R, P, Q, back to R is going 1, 2, 3, so that works out. So yes on this one as well. So that one is a correct congruent statement for the SSS congruence theorem. So this is just an interesting question. I like this one because it talks about a little bit of a construction model. Just in real life, if you were to construct a bench, which one would be more stable? And here's where the SSS can kind of help you, because you have two congruent triangles on this guy over here with this board really kind of going at a diagonal from one corner to the other corner, creating two triangles that are congruent. And this one doesn't have that board. And so it's saying, okay, explain why the bench with the diagonal support, this guy right here, is stable, why the other one here could collapse. So this one could collapse. Doesn't mean that it will collapse, because you would still probably put screws into here. You know, you'd put your screws in here, and maybe put the screws from the top if you want to screw it all together. But the thing about that is, with no support, it could shift back and forth, definitely over time, for sure. The screws would probably get a little looser as people would sit down and move around on the bench. And eventually, yeah, they would get looser and looser, and eventually, boom, they're going to fall on their tuchuses and be on the grass. This one here, however, with this support, so you still screw everything in, but then you're going to screw in this support right here. This one will probably be screwed into the top. This one will be screwed into the bottom here. And so throughout the time, as people come and sit down, get up, sit down, move around, that's never going to change. That's always going to stay the same. No matter what, this is not going to collapse over time, because you have the support there. So that's what this is saying here. The bench with the diagonal support forms triangles with fixed side lengths by the SSS congruence theorem. These triangles cannot change shape. So they will not change shape. They'll always be congruent, which means it's always going to be stable. The bench is stable. With the bench without this diagonal support is not stable, because there are many possible quadrilaterals with given side lengths. So we could change the shape of this quadrilateral, and it would eventually collapse. It could become a parallelogram, and if it did that, it will eventually collapse. So just going off of that example here, it says determine whether the figure is stable. So number 4, is this figure stable? If you were to put 4 boards together, you have a quadrilateral like this. And if you do not put any diagonal support through here, these could change shapes. You could make a parallelogram out of this, and it's not stable. It could collapse. So no, it's not stable. The square is not stable because there's many possible quadrilaterals, which means, quadrilateral is just a 4-sided figure. It doesn't mean just a square. Square is not going to maintain that shape. It could become a parallelogram or anything else. So number 5, it has your quadrilateral, but it has this diagonal support here. So it has these 2 triangles right in here. And so this one is stable. Diagonal support of the figure forms triangles with fixed side lengths. So by SSS congruence theorem, these triangles cannot change shape, so the figure is stable. So that would be stable because you have a triangle here and a triangle here. Number 6, you do have a triangle in this one, but then you have a triangle and a quadrilateral. So with the quadrilateral, that doesn't make it stable. You have to have only triangles. If we had another support in here, we could have 3 triangles, and that would have been stable. But with only the 1 triangle and a 1 quadrilateral, then no, the diagonal support in this figure forms a triangle and a quadrilateral. So that's why the quadrilateral has many possible quadrilaterals to it. So that could definitely change shape there. So now that you've seen all that, you definitely should know what we're going to answer this with. Determine whether the figure is stable. Is it stable? So you should be able to tell me whether that is stable or not. It does have the diagonal support. It has the 2 triangles. So yes, of course, that is stable. By the SSS congruence theorem, the triangles cannot change shape. So go ahead and write that down. Write down that these triangles cannot change shape. Say yes. Diagonal supports in the figure form triangles with fixed side lengths. The triangles cannot change shape, so yes, the figure is stable. So write something like that down. Definitely say that the triangles cannot change shape. All right, let's pause a little bit here for our joke of the day. Who helps the little pumpkins cross the road to school? That would be the crossing gourd. That would be a lot funnier if you know VeggieTales, because the gourd is a squash, kind of a type of squash, and actually a pumpkin is a type of squash as well, or zucchini or something like that. It's from that same family, but yeah, it's a gourd, crossing gourd. Okay, so we're going to go back to 145. Look at our vocabulary. It has two there. It says legs and hypotenuse. This is specifically for a right triangle. So in a right triangle, the sides adjacent to the right angle are called legs. So you want to write this or copy this down here, the shape, the actual diagram. That always speaks a lot louder than just the words. Picture, draw the picture. So you have your right triangle. Here's our right angle. The sides adjacent to this angle are called the legs. And then the side opposite the right angle is called the hypotenuse. And so you want to write down the words. So you could say for legs, that would be the sides adjacent to the right angle. And then hypotenuse, you would just say that's the side opposite the right angle. And then draw this figure down here so you can see the picture. So the hypotenuse is always opposite, the side opposite the right angle. So here you have a right angle. These are always perpendicular. So these two perpendicular ones are the legs, and then the diagonal one there is the hypotenuse. So now using that right triangle, we're going to be able to do this theorem here, still on 145, just right at the bottom. You'll see the HL congruence theorem. So here's another one. It doesn't use S and A because it's specifically for a right triangle. If you have a right triangle, all you need to know, or just to be able to tell, is the hypotenuse and a leg. So it says if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of a second right triangle, then the two triangles are congruent. And so that's what we see here on our diagram. We have our right triangles there. So here's your hypotenuse. Those, the AB and DE are the hypotenuses. Those are congruent to each other. And then a leg, AC. DF, those are your legs that are congruent to each other. That's all you need to be able to say that these two triangles are congruent. Is just a hypotenuse, hypotenuse and one leg. And so again, these are shortcut ways to be able to prove triangle congruence. So we saw SSS is one way, and now if you have a right triangle, all we can just do is the hypotenuse and leg. The H and the L is another way here. In a couple of lessons ago, we saw the SAS as another shortcut way to prove triangle congruence, would be side angle side as well. Okay, so our last couple problems on the extra practice are going to be proofs. So I'm going to have you watch these two proofs. We're going to go through two of them here. You don't need to copy these down. We're just going to watch them. These are in the textbook. So here's our triangles. It does have a shared side right here, which is always, going to be congruent to itself by reflexive property. It does say that we're trying to prove that these two triangles are congruent, and what we're given are two sides up here. So the KL and the NL up here are congruent, and then also KM and NM are also congruent. And so we could start off by just writing down what the given is. So we could start with the first given, the KL and NL. Those are given as a side, so we can use S for that one. So we can use SSS. We're trying to use the SSS or one of these shortcut ways, and since we see it's all about sides, there's nothing in here with angles, we're going to use SSS. We have another S right here from KM is congruent to NM. So there's two S's. We need the third S, and that's what I was telling you at the beginning. LM is congruent to LM because of the reflexive property. So now we have SSS. We can now say the prove part. That's our next statement is the prove, and the reason would be the SSS congruence theorem. And there you go. So not too hard to do the proof there. Just got to be able to write down the S's here. You got to get all three S's, and then you can write down what you're trying to prove with that SSS congruence theorem. So anytime you're trying to prove something with the triangle congruence, use one of these shortcut ways. Figure out which one you can use and figure out how to do that, and then write it down at the end. Okay, so here's our next proof. Just again, watch this one. This is also in the book. What we're given is, so we have a couple triangles here, actually almost like three triangle little ones here, or you have the two big ones, and I think let's just look at what we're trying to prove here, that WYZ, that's the big one here, is congruent to XZY. XZY, that's the other big one here. So we're looking at those two triangles, definitely identify what you're trying to prove, which triangles you're trying to prove are congruent. So what we're given is that WY is congruent to XZ. So WY right here is congruent to XZ. So these diagonals are congruent. Those are congruent to each other. We're also given that some things are perpendicular. So WZ is perpendicular to ZY. So WZ is perpendicular to ZY. That makes this a right angle right here, making it a right triangle. And then XY is perpendicular to ZY. So XY is perpendicular to ZY right here, making that also a right triangle. So these are two right triangles according to the perpendicular. But we would need to actually say that. We can't just, assume that. We would need to actually say that using like the definition of what right angles are. So as we start to build this, let's start by figuring out, what is our thing here? So one thing it says to do here is redraw it to two separate triangles, because it might be easier to work it out on paper here instead of trying to just think of this all in your head. So writing out the two separate triangles is definitely helpful to see that, and then labeling them separately. And then just labeling what we are told in the given. There's our congruent sides, there's our right angle. We do know that those are right angles because of the perpendicular. And so now when we start to prove it, we can start off with the side that we know. So we know since it's a right triangle, we're going to try to use the HL, hypotenuse and a leg. We have the hypotenuse right here. The WY, the XZ, that's the hypotenuse, that's the side opposite, the right angle. So there's our H. And then we can also show down, here's the other given. We're given all the perpendicular stuff, and therefore we can then say that angle Z, angle Y are right angles. That's the definition of what perpendicular lines are, that they form right angles there. And so then, because of that, if we know that those are right angles, then we could say that these are right triangles, that the two triangles are right triangles, and that's a definition of a right triangle. The definition of right triangles is that it has one right angle in there. So all of that is to be said so that you can now say, that this is a right triangle, to use the HL, really. And so now we're going to go ahead and look at our last one here for the side, and that would be the shared side here at the bottom, that this is a shared side. So we can now say that this side is congruent to itself. ZY is congruent to itself. ZY is congruent to YZ right there, and that's the reflexive property. Therefore, now that we have the H and the L, we can now write down the two triangles that we're proving are congruent, put the proof part down here, and we could say HL congruence theorem on the other side over for the reason. That's it. Okay, so on page 147, here's this proof. Number 6, it does say to redraw it, which I was saying that's a helpful thing to do. You can redraw this to two separate triangles. It does share the vertice there at B. It doesn't have any shared sides, but it does share this vertice. So you can redraw this, and there is two separate triangles. They're both right triangles, so if you know they're right triangles, you're thinking right away hypotenuse leg theorem, H and L. So start by, you should have your little thing here with statements and reasons. Start by writing down the given, and that's number 1 to put down. So write down this here, right, given for the reason. And then we have 4 of them here. You can see we're going to be doing 4 of them. And we obviously know the last one will always be our proof part, so we should know what's going to be down here. But how do we go from number 1 down to 4? So first of all, we're trying to prove that these two triangles are congruent. We separated them in here. It tells us in the given that B is the midpoint of CD. So if this is the midpoint right here, that tells us that this is congruent to this, that these are congruent to each other, because that's a definition of a midpoint. So we know that. We're told also in the given that the AB and EB, these are congruent to each other, and those are the opposite of the right angle. Those are definitely hypotenuse right there. That would be your H. And so we can even start right from the given. We already got an H from that, with that congruent side there being the hypotenuse. So there's an H. Also says that these are right angles here, so angle C, angle D are given to us, that those are right angles. So as we start to build this down, we can go off of number 2, that BC is congruent to BD. So we know that BC right here is congruent to BD. And that's because it said in the given that B was the midpoint. If that's the midpoint, that's right in the middle. That cuts this into 2 equal halves. So those means those are congruent, and that's just the definition of what a midpoint is. And then number 3, so from right there, what do we have? We have actually our L. That's congruent. So that's really our L. There's our H and our L. But we would want to then, say that these are right triangles, though, to be able to use H and L. To actually be able to use the hypotenuse leg, we need to say that these are right triangles, because the given only tells us that these are right angles. So we need to say that triangle ABC, that these are right triangles, and that's just a definition of a right triangle, right? That's the definition of what a right triangle is, that it has a right angle in it. And now we can say the prove part, and now here's where we use the HL congruence theorem over here, and that's the end. HL congruence theorem is our reason for it, because we've found the hypotenuse and the leg both being congruent on a right triangle. Okay, so here's our last one, number 7. So using this diagram over here on the side, looks like kind of almost 2 hourglasses next to each other. So let's first figure out again what triangles we're trying to prove, because there's a lot of shapes inside this figure. Which 2 triangles are we supposed to be focused on? E, F, G. So here's E, and then there's F, and there's G. So it's this triangle here. I'll go and highlight. You can go and highlight on yours as well. That's this triangle. And then the other triangle is H, I, and J. And I'll use a different color here. Maybe go green. Maybe I'll go green. And so that's going to be H, I, J. So H is down here, I and J, so that's up this way. So there, across there, and down here. So those are the 2 triangles that we're focused on, showing that those are congruent. Shows us a lot of the stuff in the given here is congruent. A whole bunch of things are congruent. So all these little 1 marks, they're all congruent to each other. So a whole bunch of equilateral triangles in here. You have a whole ton of equilateral triangles all in here. A whole bunch of little ones. And in fact, what we have for even our big ones, these are equilateral as well, because each of these sides here is 2 of these marks. So this is the same as this, which is the same as that. These big ones are even equilateral. So the first thing is to write down all the given. I know that's a bit to write, but go ahead and write that for number 1. You see we're going to have 5 of them here. So number 1, write the given down. And then for number 2, so now that we go into there, we now can be adding some things up together, because we want to actually now talk about, these are all kind of separate sides here. We can now add these 2 together and show what they equal. And so we could say, okay, EF, right here, E to F on the yellow one, is these 2 sides added up. So those 2, EK, KF, I know there's a lot of writing to do. Just go ahead and do it as best you can, or write it all down. This needs to be all written down here. FG, so basically got to talk about each side here. So we got EF, FG are these 2 added up, and then GE, that one are these 2 added up. So you first talk about the yellow one here that I highlighted, that they are all these 2 sides added up here, these 2 sides, and then do the same thing on the green. So the green here then starts talking about HI. So HI is this side here, that's the HK and the IK, or KI, added up. And then it talks about IJ at the top here. It's these 2 sides added up. So it's the IE and EJ. And then over here, this side right here, the JH, are these 2 sides added together. So that forms all of those. And what we're doing with that, what we just did? Well, we just added segments together. And that's just a segment addition postulate that we learned way back in chapter 1. Just adding segments. 2 segments formed to give you a longer segment. You added the segments together to get you a longer segment. That's just segment addition. So you're just sometimes going back to everything we've learned in the past. You still got to remember that. segment addition postulate from chapter 1. Now number 3, we're going to kind of put these together now. So going back here, we got EF here is equal to EK plus KF. So right here, EF is equal to 2 times EK. Well, how did we get from here, this little statement right there, to this statement here? So remember back up here that EK and KF, that they're all congruent. All of these are congruent to each other. So we can actually substitute in EK for KF, and now we have 2 EKs is equal to 2 EK. We can do the same thing for basically all of them. FG is equal to 2 EK. We can just keep using EK. Now they just chose to use EK. Why they choose EK, I don't know. You could have chosen any of these other ones to use, but they just chose E and K. Maybe because it was the first one that they used right here, possibly. So they all, FG is equal to 2 EK, GE is equal to 2 EK, and the same thing goes all the way through it. So again, what did we just do? We just did the substitution property. We substituted EK in for all of these. EK here, that means 2 EK. These are both also EKs. EK was substituted in for these two, so now 2 EK here. So that's what we just did. And now we come down to number 4, where we can now start to talk about that certain things are going to be congruent to each other, because if they equal 2 EK, if everything equals 2 EK, then they're going to be congruent to each other. So we have HI on one triangle, so the HI is this one on the green one, is congruent to EF, so EF would be here on the yellow one. And you can see as you look at your proving part, HI, EF are the corresponding sides right there, because they're both the first two. FG, IJ, there's the next one. Those are congruent to each other, and we want to put them showing congruent to each other, even though that, obviously everything is congruent to each other here. We know that because they're equilateral, but we want to do it in a way that would work with this congruence statement. And then we can see the E and the G is going to be congruent to H and J, and that's what we have here, or GE they used, and JH. Those are congruent to each other. And so then we went from here to here, so we got to figure out how did we go from here to here, and that was just the transitive property of congruence. So again, if this equals this, then that equals that. So obviously if EF is equal to 2 EK, FG is equal to 2 EK, then these two are equal to each other. You can use that with these ones, HI and EF. We did that with these two guys right here, putting those congruent. Just transitive property for each one, basically. And now what we just have here, if this is congruent, what we have is a side for this one. Here's another side for that one, and we have a side for this one. 3 sides, then we now can say these are congruent by the SSS, congruence theorem, because if we just figured out the 3 sides of one triangle are congruent to 3 sides of the other triangle right here in this number 4. And so then we can just put our proved part down there, and the reason is the SSS. All right, so that concludes our lesson here on 5.5 with the SSS and the HL. And then you want to go on to the assignment, and I'll see you on the next lesson.